Okay, I'm going to sit down at first because I'll be flicking through the slides from last time, just as a quick recap and maybe inspire any questions you might have or thought about over the long weekend. Yeah, so we talked about just why is uncertainty necessary in deep learning? Why can't we just do with point predictions? And the general idea is for kind of higher order kind of control and awareness of the environment. And so in self-driving, again, just to repeat the example, like, right, if there's a blinding light or some sort of distraction or something that confuses us, right, uncertainty can tell you how to slow the car down and maybe prevent an accident. And we see that neural networks, I showed this example, are just vanilla kind of traditional neural networks can be quite vulnerable to changes in their environment. So even just taking MNIST and rotating a bit, the network can be very confident that it goes from a 3 to other digits like a 4, right? And of course, we don't expect the neural network to perfectly generalize over all rotations, but we ideally want it to be at that red bar, maximum uncertainty, saying, I don't know what I'm seeing, therefore I predict 1 out of 10 equal probability over all classes. Yeah, and we talked about the regression setting and maybe got a bit more visual by thinking about just one neural network fits a line like this. Of course, if it's a data well, but we don't know what it's doing in between the data or areas that we've seen the data. And things like Bayesian neural networks, by integrating over this posterior distribution on the weights, can give us a sense of how the weights could have been different in those areas. And that gives us uncertainty bands like we see here. We talked about the model definition. And at the core, it's really just traditional Bayes rule. We have the likelihood, that's the usual neural network term, times our prior on the weights divided by the marginal likelihood. And of course, like all Bayesian inference, the marginal likelihood is what makes it difficult because we have this high dimensional integration problem. So today we'll talk more about how we get around that. Yeah. I talked about priors and kind of there are two big principles about these priors. One is we can analyze them by thinking about their infinite width limit. And normal priors that are by far the most common prior used converge to something called a Gaussian process, which is just very smooth, non-parametric regression line. And this happens in practice, we showed. So it's something you should think about because it does have impacts in the sense that theoretically the hidden features will sort of be diminished in this Gaussian process limit. We also thought about how to put hierarchical priors on the weights to maybe get around this Gaussian assumption or these limitations from the Gaussian. And one simple thing to do is just to put a prior on the variance of the Gaussian or the scale here. And to inform how we set this, we can think about the architecture and maybe it's most interesting in things like residual networks where we can think about for all of the weights in one layer, sharing the variance such that they all kind of grow and collapse at the same rate. And something like a ResNet, this has the effect of actually allowing Bayesian inference to select how deep we want the network. And these hierarchical priors also have a nice theoretical property because they don't correspond to Gaussian process infinite limits, but rather these more interesting jump processes that allow us to radically change the function that we're learning. Yeah, we also talked a bit about discrete priors, and you know, these are certainly interesting and could be useful for computational efficiency reasons, but they provide other barriers because you don't have easy access to gradient information for training. We talked about how we might think about other architectures, like how we might think about different groups of layers or substructures in there to maybe tie them together with a variance. And lastly, we talked about how you might tune the prior, and tuning a prior is something called type 2 maximum likelihood estimation, where you actually have to integrate over your prior a bit and optimize the objective on the left. Okay. And so then we gone on to posterior inference. So now that we have the model and set the prior, how do we actually train the thing? And so the key object we care about, of course, is this posterior distribution, the probability of the weights given the observations. And right off the bat, you might think of some issues, like, for instance, non-identifiability. That is the fact that for a neural network, we can actually permute all the hidden units. And as long as we permute the weights accordingly, we end up with the exact same output. Therefore, it's an equivalent neural network. And so in our posterior, we'll have equivalent modes that just correspond to rearranging of the weights. This is something that will make MCMC sampler or any kind of investigation of the posterior more complicated because we're having to go through redundancies or redundant solutions. So therefore, you might ask, okay, what is the easiest thing we can do? That is conjugate solutions. And so you actually have a conjugate solution in the case of the last layer, because you can just think of the neural network up to the last set of hidden units to be some deterministic transformation, and we can do Bayesian inference just in the last layer weights. And so people call this a neural linear model. You might also think about to do map estimation, right? Just to train the numerator of Bayes' rule as its own deterministic optimization objective. Right, but this has this has some nice interpretations as a weight decay. But yeah, just be cautious with this because map estimates and the full Bayesian posterior often have very different solutions. And so the last major thing we talked about was Markov chain Monte Carlo. This is kind of the gold standard with how we want to get a posterior if we could. And that is we represent the posterior as a kind of mixture of particles. And we get these particles by first initializing the weights, and then for some number of time steps, sampling a uniform distribution and sampling some proposal distribution for how we should move in that space. So again, right, if we start here, we will propose some random move in this space. And roughly if it's in this direction, we'll accept it. And roughly if it's in this direction, we won't accept it. But there's some randomness to this because we sample this uniform. And so choosing this proposal distribution Q here is the hardest part. And so a much more kind of scalable and fast solution is to use something called Hamiltonian Monte Carlo. And you can just think of this as choosing these proposals of how we move based on the gradient of the posterior, which because the denominator, the hard part to compute, doesn't depend on the weights, that part falls out. So it's just like computing the two terms in the numerator, the likelihood and the prior. Right, and so now instead of just proposing some naive way to move, right, like something that's like symmetric, we'll get pulled much more strongly in the directions of high posterior concentration. And so this is what this paper did that I talked about from NYU and Google. They actually tried to get really interesting Bayesian posteriors on kind of modern models like ResNets and things like that. And so as we suspect, they are quite complicated as we see here. And then we talked about some very cheap form of MCMC, something that you kind of already maybe have done already and didn't realize it was MCMC. Basically, you can just compute the gradient of the numerator. So something like a map estimate, your map estimate gradient, but then just add some random noise to it. And this random noise causes you to follow the gradient, right? Just like we saw before. So again, just maybe going to this picture, right? If we were right here, we would be pulled towards, some mode of higher posterior concentration. But we add a little bit of noise to that gradient such that when we get maybe here, we don't get stuck, but rather we get kicked out eventually and hopefully can explore here and here and here, ideally. But you obviously have to set that noise parameter correctly. Yeah, and so here's some also some results from that Google and New York University paper I mentioned. And so what they do is they show accuracy and agreement and total variation. And so the HMC run is this big expensive HMC run that they did that we could never do with our resources. And they compared it to running SGLD, which is that procedure I showed you, stochastic gradient longevity dynamics, which is just like regular gradient descent, but you add some noise. Stochastic gradient HMC, this is like kind of the reference HMC, using multiple proposals, but we do it with many batches of data. Therefore, it adds a bit extra noise and makes your posterior computations a bit biased. Yeah, and then they have kind of a few other just different variations. And they tested kind of what is the accuracy of these methods, just raw accuracy like we would compute it normally, but also maybe more interesting is the agreement. So how do the predictions of these models agree with the HMC, like super expensive HMC run that they did? And they found that the model and best agreement was this SGHMC with secular learning rates. So it was just kind of some other tricks they used, and they found that was the best one. But the secular learning rates is important because what happens is, like, right, you turn the learning rate down, then you turn it back up again, then turn it down and turn it up again. That's important for escaping those modes, to get out of them to explore other modes. Okay, and the topic we'll start with today is variational inference. Anyone have any questions before we move on? So I think, hopefully I haven't conveyed that doing a Bayesian neural network is much more complicated than what you're already doing. I mean, it can be if you want it to be, but really if you just took, your regular neural network objective plus some weight decay, or L2 regularization, and just train that with a bit of noise, you're technically training a Bayesian neural network, right? Because you're doing this stochastic gradient longevity dynamics to explore the posterior bit with that noise. But of course, you wouldn't just train to one point estimate. You would run it for a bit and then collect kind of all these samples or checkpoints along the way. And there you have a Bayesian neural network. So as we'll see even more today, like, that's a bit of the nice thing is, like, right, you can do the kind of ideal thing and be super expensive if you want to be, or have a small enough network or data set that you can afford to be, or right, if you want to scale, you can kind of work your way back towards something that looks like a lot like what you're doing already, right? And so people, of course, have thought about this and designed it to be that way in many ways. Okay, no questions? Okay, so variational inference is an alternative to MCMC that I think I briefly talked about last time, but I'll just start it from scratch again. Alternative to MCMC, where instead of trying to approximate this posterior with just little checkpoints or particles or just little points in the posterior space, we'll actually pick a distribution, some other distribution that we're free to choose, and optimize it so that it's as close to the posterior as possible. And so just in this example, if the exact posterior, the true underlying posterior, is this purple elongated shape, and we just pick a normal distribution that's spherical, that has just a single covariance or a single variance parameter, you might get a solution like this, right? Where sure, it captures something about the true posterior, but clearly there's some approximation error as well. But the point is that this is much faster to optimize and is going to work in high dimensions much better, right? Because if you imagine this was in millions of dimensions and you just have these little point estimates everywhere, you're not going to get a lot of information for every point estimate. But if you can fit whole distributions that are covering the space, that might have a chance of scaling to higher dimensions. Okay, how many have seen variational inference before? I know it's in some of the other tutorials on, so no one? Okay. So I guess this is taught in machine learning 2, or advanced machine learning, but Patrick's course. I guess that's maybe why you haven't seen it yet. Okay, so I'm going to give a very neural network centric view of this. There's kind of a lot of other things you can do. But again, if you just remember that first slide, we're going to fit a distribution to approximate the posterior. That's the whole idea. So if you hear variational inference, there's just some sort of approximate distribution being formulated and optimized. But one thing we have to do before we start is that instead of having this approximate distribution over all layers, kind of jointly, we usually assume some sort of simplification, some sort of independence assumption. Um, so so right, because imagine if you fit a normal distribution, say, hey, okay, I want to take a normal distribution, and that be my approximation. I want to have a full covariance matrix over all the weights. Right? If you recall from last time, the covariance matrix in that case would be number of parameters by number of parameters, right? It'd be huge. It'd be million by million matrix we'd have to store and optimize. So we want to break it down a little more simply and say, okay, maybe instead of having this full joint distribution over all of the weights, we'll have it factorized. That is, will just be a product over each individual weight. Sorry, individual layer. And you can go even a bit further. And so the mean field assumption is you say, okay, I want to break this down. So I'm only fitting a distribution over every weight individually. So you break it down over layers, L, and then dimensions, DL. So as you might see, this is already super naive, right? Because it's like every posterior on a weight is not talking to every other weight, right? You're not learning any kind of covariance or dependence information, right? Where in reality there would be. But of course, we do this for the sake of scalability. And it's just not too bad assumption. I think this name, I don't know if there's any physicists in the room, I guess the name mean field comes from physics, another physics interpretation of you have some interacting particle system and you kind of assume that each particle is relatively independent. That's where that name comes from. And so again, as you might have guessed, often people just pick normal distributions for these approximations. So something like a normal distribution over every layer or a normal distribution over every weight. Okay, so how would we fit this then? Ideally, we want to fit the following. So know that these are the parameters of these distributions. So what we have to do is find the mu and sigma that makes this distribution best approximate the posterior, right? So those are the parameters we need to optimize. And so we want to fit, ideally, this optimization objective, where we take some divergence function, that is, it tells us like how close one distribution is to another distribution, between the posterior, or approximate posterior Q, and the true posterior PW, right? Ideally, this is what we want to do. And this could be like a divergence if you've seen KL divergence before, or there's other types like Hellinger divergence, things like this. But you know, what's an issue with this already? So this should be fine. We can pick this. This is fine. And we can pick this because we can pick any approximation that we want as long as we think it's good. The problem is going to be right here, right? Because if we knew this already, we wouldn't have to do this in the first place, right? If we knew the posterior and could compute it easily and evaluate it, I wouldn't need to do this optimization problem in the first place, right? So how do we get around that? So first of all, for simplicity, let's just think of this as the KL divergence. This is the most common one used. And if you need a reminder, its definition is as follows. You take your distribution on the left, it's an expectation over that, and then you have a log ratio where you have your variational approximation on the top, and then the true posterior on the bottom. And again, this is just definition of KL divergence. And then you have to make the following rewriting of it. And so I'm skipping some details here, so maybe I'll write it out on the board real quick because it's a very simple derivation. Find some chalk. Right, so we have, and I'll just write Q and P as shorthand for these distributions. Q is the posterior, variational posterior, P is the true posterior, but this derivation will work for any posterior here. So I can keep it, or maybe I'll do it for clarity. Okay. And the definition that I have on the slide is Q W. Right. So again, yeah, switch that. Sorry, previous slide. This definition. And then now we know this is a function of Bayes' rule, right? This is a posterior, so we can just rewrite it with Bayes' rule. So we can just rewrite this as U W log U W times U. Sorry, this should be inverse. Oh, maybe I'll just write it. Okay, so here I just broke this apart into the QW, which is the same. And then I rewrote this as Bayes' rule, but I flipped the dimensions or flipped the arrangement because it's on the denominator. And the trick to notice here is this quantity, this marginal likelihood, this doesn't depend on W, right? So we can pull it out of the integral. And so you can rewrite this as QW log QW P. Plus, right, which this is just a constant. So when we take a derivative, it will go away. And this last step is just algebra. There's no other trick here. So maybe I'll just compare what's on the board. And so all you do here is you just, this term, this P of y given x comma w, you can pull it out of this log. And you still have the expectation here. So you have something then like plus, and once I removed this from here, I just have the definition of KL divergence again, QW, QW, PW. And so this is just KLD. So that is we have a negative log likelihood. So this is just an expected log likelihood under the variational distribution, plus the KL divergence between the variational approximation and the prior. So you might think about, why does this objective make sense? I don't know, anyone want to hazard a guess of like why this looks reasonable? And maybe tie it back to something we use already. So this first term, this is just the negative log likelihood that we would usually train a neural network with. So if I just happen to forget all this and forget this expectation, right, this is just like training a regular neural network with a point estimate. But I can't just train a point estimate anymore. I have a distribution on the weights, or this approximate distribution. So it's like an expected log likelihood. So if I just trained with this term right here and forgot about these, I'd be optimizing some sort of noisy, just regular training objective, noisy maximum likelihood estimation. But the key of Bayesian inference is, right, we get some balance between the likelihood or the data and the prior. And so the second term is saying, okay, I want to keep my divergence between the posterior and the prior close, right? So I don't want the posterior to go too far away from the prior. And so really this is just the two forces involved in Bayes' rule. One, you want to follow the data, but also you want to stay close to the prior. And so it's just mixing those two together. But the key here now is now we have this one optimization objective we can write down and just optimize this and plug it in PyTorch and let it run the gradients for us and do everything, instead of having to do this MCMC process where we, add some noise, take a step, choose whether to accept or reject or not, take another step, etc. Right. So this is just much more amenable to how we do machine learning these days. However, there's still some complications left. So this term is now easy. Usually this will just be a chaotic divergence between, say, like a normal posterior and a normal prior. This is already like in closed form. You can just look up the formula for this and write it down, or I think it's already implemented in PyTorch and all these ones, so don't even need to look it up. I think you can just get that directly from PyTorch. The problem is this term, in that we have to compute this expectation. So we have to do, again, some high dimensional integration problems, but we have to do it kind of through a neural network. Right? Again, we kind of run into the same problems of we can't integrate over the neural network easily. And so there's a very popular trick. It was actually invented here by a PhD student named Dirk Kingma, called the reparameterization trick. And he said, okay, we can't take gradients of this like as it is, but if we can write the weights as some sort of transformation of some sort of fixed distribution, then we can. And so I'll show you an example of why we can do that in a second. And so if you assume we have some transformation that says, okay, give me some sort of random number, some fixed underlying distribution to sample from, and I can transform it through G to get the weights, then I can just write the gradient as follows, where I just sample some of these and compute the weights, but then backpropagate into these 5 parameters here, right? Because these 5 parameters are the parameters of the variational posterior that we need to learn. So you probably have seen something like this before. You just haven't maybe thought about its implications for gradient-based training. But say I have a sample from a normal distribution, so we'll call this eta variable here. And say I want the weights to be sampled from, normal, some mean, some variance, and I give you a sample from this. How do you generate a sample from this, right? This is essentially the problem that we have. You can just use the location scale properties. And so you can take this sample, multiply it by sigma plus mu, and that gives you a sample W that comes from this, right? And so that's all we'll do here. And so now instead of representing your weights as directly being sampled from this in some sort of black box way, you can write it like this in your neural network. And so now when I want to take a derivative, right, I have something like dl d mu, right? This is just easy, right? This just term goes away. And then if I need to compute dl d sigma, right, this is just you hat, right? Yeah, and so uh, people have called this Bayes by backprop because it looks a lot just like gradient descent. Again, noisy gradient descent, but you're doing Bayesian inference, so Bayes by backprop is what people call it. And here's just the example I showed before. Right, so far, if our posterior distribution is some normal, we can generate our weights in our network by just taking the mean plus the scale times the sample from a fixed normal 0, 1. And this is literally the code you would write, right? So everywhere you would have your weights in your network, you would replace it with this expression. Yeah, and so, right, so we have hidden units times weights, and you would just modify your code to say hidden units times mu plus sigma times the fixed noise. And you can do this basically in general. If you know the inverse CDF, you can always just use that to generate the weights. So this is just an expression that says this always exists. But of course, you can't always compute the inverse CDF. Okay, so here's the same table I showed before, but now I've added this column MFVI, which is basically the procedure I just showed you, mean field variational inference, and we're going to compare it to HMC, these HMC solutions. And so for accuracy, right, so this was getting 89%, so this is a ResNet 20 and CFAR 10, was getting 89%, and the HMC, this got 86.45. So we took a little bit of a hit for this kind of approximation that we used. But we see the bigger gap is even in this agreement, right? So um, like these other HMC methods had about 91, 92% agreement with the HMC reference run. This only has about 88, right? So we're clearly learning different things. But maybe you might say, okay, that's actually not too bad for my application because this was just so much easier to train, and I'm happy to take these hits. And so here's just a visualization, just a deterministic neural network and the Bayesian neural network with MCMC that I showed you before. Here's the same plot, just with now with variational inference. And we see that, in the middle, it still does okay, right? It still kind of inflates uncertainty there, but it does very poorly more on these extremes. Yeah, question? But yeah, uh, I believe agreement is basically to look at the predictions generated on the test set by the HMC. So I forget if they use the actual like logit values or they use the probabilities themselves. And they say, how much do these outputs agree? So it doesn't matter if it's like they're both accurate or not. They're just saying, okay, how much do the outputs match? That's what agreement means. So ideally, if the agreement was 100%, we're saying they learned the exact same function. Uh, yeah. So I think this is fairly reflective of what you usually see, right? Like usually see just underestimation of uncertainty um, in places when you resort to variational inference. Okay. Any questions about this? If you this was a bit of a fast introduction to variational inference or stochastic gradient variational inference. It'll also come up in like the deep generative models modules and things. So it's probably not the last time you've seen it. Okay, so there's another type of variational inference that's a bit easier. So this is also variational inference, but it's much more deterministic. We don't have to worry about those sampling steps. And this is called the Laplace approximation. And I think actually someone last time, I forget who it was, actually proposed essentially this. And what you do is we'll approximate the posterior not by this kind of iterative optimization procedure, but rather we'll pick a normal such that the mean of the normal will be centered on the map estimate. So that is, we just train the neural network with the map estimate. So just get one set of point estimates for the weights. We center the normal on those, and we'll compute the inverse Hessian around the map to get our covariance. Right? And so this is the the numerator of Bayes' rule, so the likelihood times the prior. So we'll take the matrix of second derivatives of that. I say, okay, like I understand why the map estimate is sensible, right? Because that's kind of the center of our posterior. But why would we use this Hessian matrix? So the intuition is like this. So first you train to just find like a mode or ideally the map estimate. So just one point right here. So you just go here, just with regular gradient descent techniques. And then when you compute this Hessian, this matrix of second derivatives, it tells you the curvature around this point. And so we can think of it, constructing some normal around that point. And so why the derivatives correspond to kind of uncertainty is that if you think about it, what does this mean? If the derivative of if the numerator of the posterior is high with respect to a weight, what does that mean? That means that the posterior is going to change a lot as we change that weight. But then we take the inverse, so the covariance will be the opposite of that. And so the covariance will mean that we have a very low value for the in the covariance matrix here. So that means that we want that weight to stay relatively close to the map estimate, right? Because if it's the curvature is high, it's going to change a lot if we move it. Therefore, the variance should be tight. Otherwise, if this derivative is low or has a low value, meaning that the likelihood and prior don't change much as we change a weight, we'll flip it so that when we take the reciprocal, this will have then a high value. And that means that we have a large covariance, right? It means we can move a lot in that dimension and we won't change things too much. Right? So that's kind of, we get this inverse relationship between derivatives and variance. And so the Laplace approximation is becoming quite popular these days. And a big pro is that you can apply to any pre-trained model. So the parameters don't necessarily need to be at the exact map estimate. So you find some kind of big pre-trained model online, like trained by Google, or someone you don't have you have the same resources as. You can just take their weights and compute the second derivative around their point estimate, and now you have a Bayesian neural network trained with the Laplace approximation. Right, so it's super easy to apply it kind of post hoc. You don't need to actually change the training at all. But the con is that this Hessian matrix, right, this covariance matrix will be hard to compute and will be very big, right? It's going to, in the naive case, it'll be the number of parameters by number of parameters, right? So we often need to do something to break that down to make it a bit more computationally tractable. So something like a diagonal approximation. So you just compute the diagonal elements of that matrix, or something like a low rank approximation. And so I'll just talk about very briefly point you to a paper that I've worked on that I think is a very scalable approach to this. Is that we did a Laplace over a subnetwork of the weights. So you first train your weights to a point estimate just like normal, but instead of just going straight to Bayesian inference, that is computing that Hessian matrix, you do some subnetwork selection step or a pruning step. And it says, okay, so then you have to have some sort of heuristic or metric or inductive bias that tells you, okay, what's the most active subnetwork that's kind of crucial to making these predictions. And then the idea is you just perform Bayesian inference over that subnetwork. Of course, you could apply this idea to other types of variation inference as well, but it's very easy to apply to the Laplace approximation because you can just take some function of those existing weights. So here's some results. So here's the Laplace approximation if you just construct it in the full case. And so we get some good uncertainty bars in the places where we don't see data. And if you just take a diagonal approximation, so just the diagonal elements, or just all kind of the second derivatives with respect to themselves of the weights, it's good on the edges still, right? But you get the collapse of uncertainty in the middle, right? We should have much larger uncertainty there. Here's the map estimate just for reference. And if you do a Laplace approximation just in the final layer, so this is equivalent to the neural linear model, you get something a bit better than the diagonal approximation because you get some uncertainty there and a bit wider uncertainty in the middle, but still quite far from the full covariance. And you might say, well, maybe I can just pick a random subset of the weights. So if you just pick random 50% of the weights and do the Laplace approximation there, that's a pretty good inductive bias. And so you get something that looks quite like this. But that still could be kind of too expensive for a lot of modern neural networks. And so maybe you can go down to like 1% of the weights, but you use a lot of the uncertainty in the middle there. Right, and so we proposed a subnetwork selection procedure based on the Wasserstein distance. Doesn't matter the details exactly. I can point you to the paper, but the point was by picking the subnetworks a little more creatively or intelligently, we can get down to 1% of the weights and still see that the uncertainty in the middle is quite high. So we're able to capture this solution by going from 2,600 weights just down to 26 weights. Yeah, and so this, of course, is the form of a lot of modern uncertainty estimation and Bayesian neural network research is that, okay, we know what we want to do in the ideal, right? We want to run HMC, we want to run some sort of expensive procedure. How do we creatively kind of make it less computationally burdensome while still preserving the uncertainty information? And so just to wrap up our summary of variational inference, sometimes we have conjugacy. This can be useful at times. So this is the neural linear model. MCMC is possible if you have a lot of compute budget, or if you make some modest approximations like doing data subsampling, or in the more aggressive case, you do Langevin dynamics where you do something like gradient-based optimization with noise. Variational inference is much more practical than MCMC, but often you suffer in your performance based on these approximations. Cool. So okay, let's get started again. Anyone have any questions about the variational inference part? Yes. Yeah.
How do we go from that to the picture with this data set with the tree and the setting going from okay, this is a tree till this point where I don't know what
Yeah. So it's a good question. So basically, I can just write out steps a bit. Right. So say if we're so say we're doing the Laplace approximation and we're given the map estimates. Step one would be to compute normal on your training data. But right, this just gives us our posterior. We next need to get the predictive distribution. Right, that is what we actually use to generate predictions. Then we need to compute we need for some test points now, these rotated points, you would compute the predictive distribution. So y star and x star denote that they're test points. D is the training data. By plugging them into the likelihood, right? So this is just running the forward propagation, but also integrating over your map, your Laplace approximation that you computed in step one, right? So this integration is still hard. So you can you can just do it with Monte Carlo estimation. So all you do is just sample a few weights from this distribution, and so you'll approximate it as so basically I'll just sample some weights from this, and then I'll just put them into my neural network, run it, sample a new set of weights, run it again, and so then I'll get so if you want the actual distribution exactly, you can just average over those samples. So just like taking the likelihood and yeah, summing them and dividing by the number of samples. That's the easiest way to approximate this. And so yeah, so hopefully you would see that this likelihood is now more uncertain, right? Closer to 1/10 than if you were just having one deterministic point of weights. Like if you just took the map estimate exactly and hopefully, or not hopefully, but usually that is like the thing is confident in telling you it's 100% likely that it's a 4, where this will be much more uncertain. Right, but also this is just an average, but you can also do things like this is how I compute in general. Drawing samples like this and doing some averaging is how I compute, right, that predictive mean, right? You just compute the point estimate for all the times you do the forward propagation and then average them together, and then the standard deviation is just the empirical standard deviation of those values. um, um, so yeah, everything's just kind of drawing some samples and then doing some sort of empirical average of the things you get out. Yeah, was that clear? Yeah, and you actually do that in the notebook in the tutorial session, so you'll be able to see it very clearly there. Okay. So this, I mean, in the time remaining, I don't think I'll get through all of the slides, unfortunately, but they'll be posted online if I don't get through all of them. So next, I'm going to broaden a bit, not just talk about Bayesian neural networks in particular, but just uncertainty quantification and deep learning in general. And so I think an important topic that's often kind of underappreciated is just evaluation, right? Like oftentimes you'll see these like beautiful regression plots of uncertainty, but like how do we actually evaluate this to know we're getting good uncertainty in a more realistic task, or even a task as simple as rotated MNIST? Sure, I'm recording. Yeah. Right. So if we have a deterministic neural network like looks like this, and some sort of uncertainty quantification looks like this, how do we know that this one is better at uncertainty quantification than this one? So if you just wanted to compute, like mean squared error, right? If you took your in distribution kind of, maybe it's your test set, but say it's very similar to your training data, just computed mean squared error, right? Like this one fits the training data, this one fits the training data, like right, you'll see no difference, right? Because they're pretty good at fitting the data set itself. So I don't know, anyone want to venture any guesses or comments about how we can tell that this one is better at this one in uncertainty quantification? Yep. Group. Yeah, we could definitely see how much like things are varying from run to run if we do some sort of data sum sampling. Yeah. I think the key here is just think about like what do we have here that we don't have here, right? We have these error bars. It's going to be some function of those. Um, and so in the regression setting, one thing to compute is simply held out log likelihood. So when you compute the log likelihood, especially in the regression setting, like it's a function of not only the mean but also the variance, right, of your predictive function. And so right, so like if we see the uncertainty bars are very narrow here. But say I had a point right like out here, right? Like I have distribution shift or a test data point that's like living way out here. The likelihood for that is going to be extremely low, right? Like close to negative infinity, because the uncertainty bar is right, very tight. So you get penalized a lot as you move further and further away from the mean, right? Where here, right, you don't get penalized as much because, right, if I have a point here, it's the variance is inflated such that I won't get kind of negative infinitely low likelihood. I'll get something lower, but something still reasonable, right? So that's in the regression case, that's how we this observation noise is how we can quantify like how kind of tight or loose around the predictive mean we can be. And so yeah, head out the likelihood gives you a bit of a better sense of how you're doing. Um, but it's not perfect. It's also related to this notion of calibration. Has anyone seen like confidence calibration before? No? Okay, so to back up a bit, um, this is for determining if you have a black box that's generating probabilities, how much can we actually treat those probabilities like probabilities? And maybe they're numbers between 0 and 1, and we want to interpret them as probabilities. This is the case where we have a neural network, right? We do our softmax transformation, we get a number between 0 and 1, but we don't really know if that's a true probability, in the sense that if the weather person says there's 70% chance of rain, ideally, if we could rerun the day 100 times, we would see roughly 70 days with rain, 30 days without, right? That's what we want to see with a probability. And so likewise, for a neural network, we want to see if it says there's a 90% chance this is like a cat. Ideally, if we put in 100 very similar images to that cat, it says it's cat 90% of the time, something else 10% of the time. Right? So that's what we want. We want this kind of notion of like confidence and forecasting. And so you can also compute this type of diagram for neural networks, where the confidence on the x-axis is the softmax output, right? So it's the number between 0 and 1. And we can think about just doing this for the top ranked class. So we look at whatever softmax dimension has the highest value, and we can think about that as a confidence. And on the y-axis is expected accuracy. So how we compute this is that we take all of the points that say the neural network says it has 0.7 confidence in. Then we look at the test data that it says that for and says, okay, in these, say 10 cases, how many cases did it get right? And if it's roughly 7 out of 10, we know that 70% actually means something. But if it gets 100% right, maybe 10 is too small of a sample. If it's 1,000 cases where it says 0.7, hopefully that it gets about 700 right. And so you can plot these things called reliability diagrams that compare your given confidence output by the model or your predictor to the expected accuracy on data. And that's how you kind of match confidence in data and check it empirically. But note that right in reality, like I said in the weather example, we want to rerun that example or like rerun similar images through like 100 times. We don't have that luxury with a fixed data set. You could try to simulate it in some way, but really we just chop up the data says, okay, all these points that are predicted with 0.7, we should still see roughly 70% accuracy on them, even though they can be from all different classes. And so you compute this, so say just for two methods, it doesn't matter what these methods are per se, but just you might compare two neural networks. And these black bars show that like what these values actually are when they're off the diagonal. And so we see for this neural network, so method one, the confidence is quite low, right? It's like 0.5 confidence, but the observed accuracy is quite high, right near 100. So this tells you that this model is underconfident because it says, okay, I think I got this right with only like 0.5 confidence, but actually got 100% right on the data. So therefore this we would say is underconfident again because the outputs don't suggest really how confident it actually is or how able the model actually is. You can quantify how just off diagonal a model is by something called expected calibration error. And so this has 6% calibration error. Where this method 2, say, is very close to diagonal, and so it's perfectly on the diagonal here, and just in a few cases off the diagonal by a little bit over here, and the calibration here error here is under 1%. So yeah, so that's one general procedure. When the model says, gives you a confidence, gives you a value output for the softmax, can we actually interpret this as a frequentist type probability? So you can also use this to rank data points. And so given this predictive distribution value right here, ideally we want it to be right lower when X star and Y star are harder points, right? And higher when they're not, right? Like, so we want to have that model output reflect that, okay, it's near 1 when it's the easy point, and it's lower when it's progressively not easy. And so you can do something like you can just sort all of your test points by this their model output, right? So the ones that are on the top ranked have like near 1 confidence, and then it goes down from there. And you can define some threshold, so tau. And so as we move that threshold higher and higher, that is cutting off the harder and harder data points, that is, have the lowest confidence, we should see our accuracy go up and up and up, right? Because if we, again, sorted them from easiest to hardest by our model outputs, we should see our accuracy monotonically increase, because we're only then, we can evaluate the accuracy on just the easier and easier subset of points. And so this is what this plot shows. Again, just shows the accuracy on the y-axis, and on the x-axis, it's going to have some cutoff on our probability value given by the model, and such that anything that falls below a certain value we throw away. And so ideally, again, we're taking the easier and easier cases, only in computing accuracy on those. And so ideally, we should get like faster and higher and higher accuracy. And so something like, so here I'm comparing some ensembling techniques to Monte Carlo dropout. And we would say that Monte Carlo dropout here is a worse uncertainty quantifier, because it's not as good as throwing away points fast as the threshold increases as these other methods are. Was that clear? And again, maybe to tie it to an example, right? If you were given 3 tasks and you could say pick 2, if you're a good estimate of your confidence or your uncertainty, you could pick the 2 tasks you'd be better at and leave off the 3rd one, right? That's all we're asking the model to do here, is right, sort them from hardest to easiest, and throw away progressively harder cases based on whatever this probability is here. So this is also very related to active learning or data collection. So you can also have unlabeled points. And so maybe we didn't have the true label here, we just have the X star, and say, okay, given a big unlabeled pool set, I want to pick the data points which I'm most uncertain about, and therefore I add them to the training set to get a label and add them to the training set and retrain, right? So this is called active learning. It's really just letting the model kind of guide its own training by saying, okay, this point right here, if I had the label for it, this would be most helpful to me. And so you can make plots such as like the number of labels collected on the x-axis and the test accuracy on the y-axis. And again, a method that's better at quantifying uncertainty, as it collects more data, it should get better and better accuracy. So here's the red line is a Bayesian method, the blue line is a non-Bayesian method. We see the Bayesian method gets quite higher accuracy, around 300 label points, right? And because it was able to learn faster, it was able to better quantify its uncertainty in collecting the data in the first place. So yeah, so I mean, you should be noticing a trend here that's right. Uncertainty doesn't just give us like, is your prediction better or not, but it kind of tells you, okay, if I'm allowed to take kind of actions around that decision-making process, I should be able to do that better. And so like kind of ordering your data points from easiest to hardest, collecting more data, things like this. And so related to this is what I was stressing before is like, right, we want to evaluate this based on the areas we haven't seen data. right? Because those are the cases where it should be the most different from a poor uncertainty estimator. And so yeah, this is the plot you already showed a bit, but right, again, maybe you have some sort of progressively corrupted data set. So again, this is like angle of rotation on MNIST, but you're rotating MNIST more and more. You want to plot the entropy of your predictive function. The ideal classifier should get more and more uncertain in its entropy as the data becomes more and more corrupted, right up to like max entropy ideally. And you can think about this like this angle of rotation here. It would be something like akin to like starting here and then moving more and more and more to this space, right? That's essentially what we're doing when we add this gradual corruption. And so here's some plots they took from some different papers. But basically, they have rotation on the x-axis, and this is corrupted CFAR, so just progressively harsher corruptions on the x-axis here, right? And they show log likelihood, and so you can combine these two things. Whereas we ideally here we want methods to actually have higher log likelihood as it becomes more and more corrupted, because it means that they were able to put more uncertainty in those corrupted areas, and therefore their likelihood doesn't go down to zero, or sorry, negative infinity as fast as other techniques. That's kind of combining the two ideas of out of distribution and likelihood. So just a quick summary at this point, like prediction alone is usually not sufficient. You want to use it for kind of second order tasks or decision making. So things like ranking data points, collecting data, abstaining on data points, and then evaluating under distribution shift is a crucial way to do this because right, it allows you to move from those areas of high density to areas of low density and see how the distribution changes as you make that move. Okay, any quick questions about that? Okay, so another very cheap uncertainty estimation technique is just simple ensembling, which you've probably seen before, I assume. So here's these three uncertainty plots that I showed earlier at the end of the variational inference section. If you just take an ensemble of 5 neural networks, and that is input the same input, so these were all trained independently. So say we have 3 neural networks, each were trained starting with a different random seed, so they converge to different solutions. And for a given input feature, we just put them all into these neural networks and see what they predict. So maybe 2 agree, but 1 disagrees, right? So it's an 8. We can use this as a notion of uncertainty, right? And it's super simple, right? It's expensive because we have to train multiple networks, but right, there's nothing else to it other than that, right? It's just letting the different random seeds or different randomness in the training processes give us different solutions. So people call this a deep ensemble. And if you evaluate the uncertainty with a deep ensemble, it actually is quite good, right? So it's not quite as good as the MCMC solution, but right, if you compare it to variational inference, it's actually as good, if not better, right? Because we got some uncertainty in this middle region and also some uncertainty inflation in these n regions. And so why does this happen? So if you think about training one neural network, right, it looks something like this. But if you train 5, what happens is they'll all agree roughly in the places where you see data, but because neural networks are so over-parameterized and flexible, they'll all do different things in the places you don't see data. And so that's what you see here, right? Like the red line goes up, the purple line goes down. Right here, the purple line goes up, the blue line goes down. Here, the purple line goes down, the red line goes up, orange line goes up, right? And so when we compute a uncertainty over ensemble, all we are doing is averaging over these different ways the line can move outside of the data. And so here you compute the same thing as here, but instead of having different samples of the weights, right, this would just be for my number of ensembles. So if I have 5 ensembles, S would equal 5 here. And I just plug in the 5 ensemble weights. That's all you have to do. Yeah, and so here's the again, just here's the uncertainty for 5 ensembles. So is that? Oh yeah, question. Sorry, say it again. Yeah. Roughly here. I mean, this is a real valued regression case. Um, so you could do it two ways. I'm guessing the most proper way to do it is to take one ensemble, put the X through, and sample a bunch of labels from it, and then do that for every ensemble. And then now you have a collection of real values that like sit along some kind of particular X value, and you compute the mean and the standard deviation of those, and that gives you these bars. Sometimes people don't do that extra step of resampling predictions. They'll just take like the mean and you average the means across the 5 ensembles, or and then you take the standard deviation across the means. That will also give you something here, but that's a bit less rigorous, and I'm guessing will underinflate your uncertainty a bit. But yeah, it's super simple. It's like 5 neural networks, draw some predictions from them, just take some average or whatever kind of statistics you want to get that. Okay, everyone understand? I think this is like if I had to give you kind of one tool to take away here, this is it, right? So it's just maybe a tool you already had, you just didn't know it was good for uncertainty, right? Just taking an ensemble, averaging over its predictions, and that's some notion of uncertainty, right? And again, just to emphasize, we get this because the neural networks are so flexible, right? If you just had a linear model, these linear models are all going to be the same, right? So if you average over a bunch of linear models, and assuming you fit them exactly, you're not going to have this, right? This is kind of using a negative property of neural networks, right? That they kind of learn different solutions to our advantage. But of course, right, we can think of all different ways to create ensembles. So one popular way is dropout. So how many have seen dropout before? Okay, yeah, most of you. So yeah, so if you haven't, right, dropout is just taking a standard neural network and zeroing out some of the hidden units randomly, right? And so if you think about these different configurations which we sample the hidden units to zero out, right, we can think of that as generating a bunch of different ensemble members. But instead of training kind of five networks independently, right here we're taking one neural network and perturbing it to get different ensemble components. Yeah, and so dropout, as you probably already know, was originally proposed just as a regularization mechanism, right? So in 2012, it was like this was the state of the art on MNIST, and then with dropout, people got it down much further. But now it's used for uncertainty quantification. Yeah, and so the paper to popularize this was this Gall and Garmani paper that showed dropout can be interpreted as Bayesian inference, where we take the distribution that we're sampling the hidden units from as the variational approximation. And you obtain this computation, right, in the same way. You sample a bunch of different dropout masks, plug them into your network, and then, right, you can average to get something like a predictive distribution. Right, and it had this nice picture or showed that this is generated from dropout. So just a regression problem generated from dropout. Here's your training data. Here's the part you haven't seen data before. Dropout perturbs your predictive function enough that you get a lot of kind of uncertainty after this point here. But note one thing that's weird about this that I don't like this interpretation of dropout is that um, this kind of this variation, their posterior approximation in this formulation is just fixed, right? It's just this 0.5 Bernoulli distribution that you sample for every hidden unit, right? So ideally, we want our posteriors to be dependent on data, and if you have infinite data, we want them to kind of shrink to a point estimate. But this has been fixed in follow-up works, several of which have tried to optimize this noise distribution a bit to the data. And I think when you're doing that, then it's a proper Bayesian procedure then, if you care about the interpretation. And I'll just point out, I think I have a, what my opinion is is a good interpretation of dropout as Bayesian inference. This is a paper I wrote called "Dropout as a Structured Shrinkage Prior," and this connects these ideas of hierarchical priors that we talked about before to the dropout procedure. And also kind of leans into the fact that the dropout noise is fixed, and therefore we should interpret it as a prior more than a posterior. Um, but of course, right, you just don't need to drop out hidden units, right? If we're just liberating ourselves to think about anything we can kind of average over or drop out or perturb, you can do a bunch of different things. So there's a really nice paper called Depth Uncertainty, where instead of averaging over different models, they just generate an output after every layer. And so orange shows the different colors show the different layers in the neural network. So they generate a prediction after the first layer, after the first two layers, after the first three layers, etc. So every kind of layer has an exit point, and they average over those depths. And they show that when you average over those depths, you get a bunch of different functions. And then, of course, if you compute statistics over them, you get uncertainty bars like this. So dropout drops hidden units. This averages over different different layers or different exit points in the network. And people have taken this to even more an extreme. So this is something called swap out, which was from NeurIPS a few years ago, where they switch out like ResNets with feed forward networks versus dropout for just they like just do all kind of different permutations and combinations of things and show that this can help your generalization error. And I don't know if they showed it exactly, but I'm guessing you can show that this also helps your uncertainty quantification, again, just by adding all these different randomness and random procedures. Yeah, and so so I think the big takeaway is simply just naive ensembling effectively quantifies uncertainty due to the over-parameterization of neural networks. So as long as you have some sort of random procedure to jolt it into different solutions, this is an effective tool. And basically, depending on how much computation you want to spend and kind of what makes sense for your problem, you can pretty much add this perturbation or add this noise or add this averaging to like anything you can think of, right? Different networks, different layers, different hidden units, like whatever structures you have. Okay, any questions about ensembling? Okay, in the last section I'll talk about, I'm going to change topics a bit. I mean, it's still about uncertainty quantification, but it's a new topic that's become quite popular of late, called conformal inference. And this is actually a frequentist style of uncertainty quantification. And the goal of conformal inference is to construct a confidence set over labels. So, and moreover, we want this confidence set to hold even at test time. So if I have capital N training points, I want to say something like my first test point, so n+1, I want its label to be in some set of labels that I'll construct for the input, n+1 input. And I want it to be in that set with probability greater than 1 minus alpha. Right, so just to make this a little more concrete, I want something like this, where if I have these 3 images of squirrels, all seen at test time, I want to generate, instead of just one label for them, a set of labels. And so for this picture of a squirrel, it's like quite an easy picture, right? The squirrel is centered and well lit. And so maybe so it's called a fox squirrel. I guess this is from ImageNet. So this squirrel is very easy to classify. And so the network is like 99% sure it's a squirrel. And therefore our confidence set just has one element in it, this fox squirrel. But say we get a different image, this one having a squirrel that's perched between this tree and this bucket, right? It's not as well lit. It's more in the background, right? We can't tell what type of squirrel it is. And ImageNet has like some different classes here. So you might say, okay, I still think it's this fox squirrel with 80% chance, but also I might think it's a gray fox or a bucket or a rain barrel because it's kind of seeing this, I think. Right, so now it's generated an uncertainty set saying, okay, these are the things that I think could be in this image. And maybe you have even a harder image still where you have something like this, and it might be fox, squirrel, but you also might want to put like marmot or mink or weasel or beaver also in your set. right? And so now the uncertainty is reflected in the size of this set. And I should say there's nothing, you could do this here too, right? Like you could, just like I did for the ensembling, right? You could have a bunch of your neural networks and say, what do they predict, right? 2 predicts 3, 1 predicts 8, so I have a set size of 2, 3, and 8, right? You can also do this with other procedures too. The special thing about conformal inference is that if I do it with a deep ensemble, there's really no guarantee about what this prediction or what this set means. But the conformal inference procedure is rigorous in the sense that we can actually show that the true label should fall in this set on average more than 1 minus alpha. So on average, the true label should be in here like 90% of the time. And I emphasize this is on average. So you can't say the true label is in this particular set with 90% confidence. It's like if I looked at all the sets on the test data, the true label will be in that set about 90% of the time. And so here's how the procedure goes. So say, just for the sake of argument, we have 3 classes: a squirrel, like a marmot, or like a marmot, and a fox. And we would look at their probabilities generated by the network, right? So it could be this computation, it could be a deterministic neural network, right? What's the probability of class 1, class 2, class 3? And conformal inference just simply is applied to the kind of downstream of these probabilities. So it really doesn't matter how you train this network. Conformal inference can still be applied. So you can actually kind of compose it with something like a Bayesian neural network if you really want to. And so what happens is, for every point in your test data, or sorry, a validation set, you're going to look at these probabilities and say, I'm going to add them to a statistic until I reach the true class. And so if the true class is class 1 and this is the highest probability, I would stop there. I would just add that to my statistic. If class 3 and is the true class and they're ranked this way, I would add probability of class 1, probability of class 2, probability of class 3 all together. And so for every point in the validation set, I get this sum of probabilities. And then I will take the empirical quantile, alpha quantile of these scores to say, okay, I want some threshold that says, okay, for 90+% of my validation examples, I contain the true class in that score. And then we'll use that score at test time to construct the prediction set, which I'll now show. And so at test time, for a new data point, we re-rank these classes in descending order. So say probability of class 3 is top ranked, probability of class 1 is second ranked, probability of class 2 is third ranked. And we will keep adding them to the set as long as the sum of the probabilities doesn't go over some threshold that we computed on this validation data. So maybe you had the first one, a fox, and you check if the probability of fox was greater than the threshold. Let's say it's not, but if it was, we'd stop there, just like we got a set size of 1 before. If it's not, then we'll add the second ranked one, squirrel, and check if the sum of the probabilities goes over this threshold. And say it doesn't, so we stop there. And this is our set. So super simple. And you might say, oh, it's kind of amazing that with such a simple procedure, we can actually say anything stronger about it and say that on average, the true label will be in the set with some probability. And really, this comes just simply from using validation data to get this quantile. If you assume that your data sets are from the same underlying distribution, there's some mathematical underpinning that says, okay, if you compute this quantile in validation data, it should kind of hold forevermore on test data as long as it's coming from the same distribution. So it provides some nice rigor to using a validation set, but there's nothing kind of magical happening. It's basically just assuming your validation set is reflective of your train set. And therefore, if you compute this quantile threshold on the validation set, you can say things about the test set kind of forever. Yeah, and so this will also be in the tutorials. So in the second tutorial, Alex, who is doing his PhD on these topics, will tell you more about them and also compare them to some of the other techniques on a regression task. So you can, so I just talked about this for classification, but you can also apply it to regression. And so it can be quite nice there as well. Here's a regression problem. And so the conformal approach gives you these error bars, even for this tough regression problem where it like splits, where some more traditional approach wasn't able to do that. Yeah, so the summary of conformal inference is that you construct these uncertainty sets without any significant modification to training. You can do it all after the fact. The price you pay is invalidation data. You actually get a marginal coverage guarantee. That is, you can say the true label is within this set on average some percent of the time. And one of the big problems, though, in practice is these sets can often be quite lot wide or large, and so you have to do some work to like get them a bit smaller, a bit narrower. Cool, and I think that is my last slide. So I'm not sure what happened to my Zoom. Thought I was recording, but yeah. So I'm happy to take. That's all the prepared slides I have. These will be posted online. Happy to chat for 5 or more 10 minutes about any questions you have or any of the projects available. Yeah. Yeah. Yes. So like for this procedure, so say I want to evaluate them based on ranking. I mean, so I first should say that there's no like one number that tells you what's better, right? First, you just want to do raw accuracy or raw predictive performance, right? You just want to make sure it's a good model in the first place. And if it passes that test, then you care about these kind of second order things. And so one could be, again, like ranking data points from easiest to hardest, right? Because if a model is accurately quantifying its uncertainty, it should tell you, okay, this is a hard example, this is an easy example. And this procedure, right, all it needs is this probability of p of y given x, right? So it just needs something like this or like this, right? So it doesn't matter how I get that. I can get that ensemble, I can get that from Bayesian neural networks, and I can compare them in this task just like that. So that's why it's usually all in terms of the predictive distribution. Where you wouldn't have where you'd have a mismatch would be like if I want to compare ensemble to a Bayesian neural network by like trying to look at the weights themselves. That wouldn't make sense because right, like the weights don't really mean anything, and maybe you could say, oh, I'm getting closer to the posterior on the Bayesian neural network, but even that posterior is probably hard to know you actually got the right one as a reference. Like, so usually people just think about predictive uncertainty and how do I do things like data collection, data ordering, abstention, things like this. Is that clear? And yeah, I should say for conformal, I can do the same thing here, right? Like I could order my points based on the size of the conformal set. And so the ones that have the highest conformal set, I can throw away first. And so this could be like set size on the x-axis. So I just start with all the data points. I throw away the ones that have the largest conformal set. I compute the accuracy, and hopefully that would continue to go up and up and up as I restrict myself to ones with smaller and smaller sets. Yep. Um, yeah, maybe honestly, I know very little about quantum computing, so I guess yeah. On one hand, you could maybe compute the posterior better, but like if you're maybe in that case, you can probably just do like things like deterministic search for solutions like a lot faster too. That maybe you don't even need a model. Yeah, I don't know. Good question though. I mean, like someone was asking me about this earlier, like if you had, or last week, if you had some notion of kind of fundamental uncertainty in your computation, can you use that to your advantage in some way, maybe by computing a Bayesian neural network? And I said, yeah, this is done. Like, so for instance, for privacy, people often add noise to data or noise to the model parameters. And so you can show this link between adding noise and doing Bayesian inference. So there's a paper called like privacy for free, and doing doing some sort of Bayesian inference gives you some notion of privacy for free. Maybe you could apply it to quantum computing if there's some sort of uh, uncertainty in the underlying computations, or if you just had a noisy system in the first place. Yeah, I think, I mean, hopefully you found this topic fairly important. Like, I think if you're working some sort of job, like anywhere you have predictive models, right? And you go to your like boss or the business people and say, hey, I think we should like do something, right? I think we should, order this many units, or I think we should, do whatever. They're going to ask like, how certain you are, right? And so hopefully some of these tools can help you answer the question. Right. Same way if we want to bring like AI and machine learning to healthcare, right? Like, one of the big obstacles is these systems being black boxes. And so if like a doctor tries to use them and read them and only sees like, oh yes, this person, right, like has a disease or does not have a disease, right? That means nothing to them, right? So if it says, oh, it has a disease with 99% probability, right, that already means a lot more, and it's something they can go further with. Yeah,
I think in those cases, it needs some kind of expensive.
certainly, yeah. It's not it's certainly not the last thing. Yeah, it's just more. I'd say it's like you want the prediction first, and this is like the second thing you want. Yeah, and maybe explainability then is third after that. But yeah, but it can also, I mean, so maybe it doesn't inform the final diagnosis, but it can be something like, oh, like it can help with data collection, right? Say, hey, like doctor, this patient hasn't doesn't look like the patients in the clinical trial that this drug was evaluated on. Like we shouldn't give them this drug, or maybe something like that, right? Maybe it's not like a yes or no diagnosis decision. Maybe it's more of like telling the doctor things that they couldn't easily kind of know just from even reading the like a one paper and the patient, right? It's kind of large scale data driven things like that. It can, yeah, 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 anomalies, yeah. Yeah, so I mean, so again, just going to the conformal inference part, that's easy to think about. Ideally, if you have an anomaly that goes into your system, you want that set size to be the number of labels. So, right? If it's MNIST and I put in a chicken, I want to generate a label set of 10, right? All the digits because it doesn't know what it is. Okay, if there are no other questions, let's wrap up there. And yeah, thanks for attending both early morning sessions and yeah, hope to see you at the tutorials. Well, I won't be there, but I hope you come to the tutorials and take one of the projects. And while the TAs will be leading the projects, like I'm happy to consult as well if there's any kind of questions on how to proceed or anything. So yeah, thanks.